Good evening and welcome back to this problem solving session for the NPTEL course Geology and Soil Mechanics. So, currently we are at the end of week 4, and over this week we have learned another very important aspect of soil mechanics, that is permeability in soil. So, under this aspect, we in the very beginning we have learned about Darcy's law, which is primarily valid for laminar flow. And as you know, in most of the cases, means in most soils, the flow which is basically in the nature of laminar, and that's why this flow is governed by this law, Darcy's law. Okay. In the next section, we have learned about two different velocities, that is discharge velocity and seepage velocity. And I hope you must know about the differences between these two velocities, means which velocity is higher than which velocity is comparatively larger as compared to the other. Okay, so when we measure the velocity through a soil sample, considering the gross cross-sectional area which is at perpendicular to the direction of flow, that is called discharge velocity. Okay, but ideally or really speaking, the velocity or the flow which is basically taking place through the interconnected voids only. That's why the actual or the seepage velocity, that is termed as seepage velocity, that will be higher as compared to the discharge velocity. So this is the basic difference between seepage and discharge velocity, and you must be careful about the velocity, the type of velocity which you are dealing with in solving the numerical problems. Then we have learned about different factors which can affect the permeability. So mostly the soil matrix, the properties of the soil matrix, and the properties of permeant, that is the fluid which is basically flowing inside the soil matrix. These two factors majorly affect the permeability. Then how to determine the soil permeability? So there are two types of tests available, or into different ways we can determine the permeability. So these are, either we can perform the soil permeability test in the laboratory and we can determine the coefficient of permeability known as hydraulic conductivity, or we can perform the test in the field itself and we can also determine the coefficient of permeability. So now under this laboratory test, there are constant head permeability test and the falling head permeability test. So we'll see what are these tests in the uh, due course of this session. And under the field test, there are this pumping out test. So different tests are available, so by which also we can determine the coefficient of permeability. So apart from these two tests, means laboratory and field test, there are some empirical equations also available in the literature by which we can also determine the coefficient of permeability. And lastly, at the end of this week, we have learned the concept of equivalent permeability in the case of stratified deposit. So initially we started discussing about the concept of permeability in a homogeneous soil, but when we basically uh, faces or we face this type of geological deposit, and it is the feasible case, the most feasible case in the real scenario, something deposit like this, means the soil is basically deposited in a layered fashion. So in this case, the coefficient of permeability changes for each layer along the direction of flow. Okay, so that's why in that case, to simplify the calculation, we have to use the concept of equivalent permeability for this kind of stratified deposits. We'll also solve one problem on this aspect. Okay, so this is a brief overview of the topics which we have learned from this week 4. Now we'll start our today's session with this problem. So here a constant head permeability test was carried out on a cylindrical sample of sand of 7.3 centimeter diameter and 16.8 centimeter height. A constant head of 75 centimeter was maintained during the test. After 1 minute of testing, a total of 945.7 gram of water was collected. Now we have to calculate, or we have to compute the hydraulic conductivity in meter per second. Okay, so as usual, we'll first summarize the given data which are given to this problem. So first of all, the dimension of the cylindrical sample will write down. Okay, so the diameter of the cylindrical sample if we mention it as small d, so it's given as 7.3 centimeter. Then the height, if we denote it as L, it's given as 16.8 centimeter. Next, a constant head of 75 centimeter was maintained during the test. That's why this test is termed or known as constant head permeability test. And please uh, note it down that this type of test is specifically suitable for coarse grained soil where uh, a feasible amount of water can be collected over a specific span of time, okay, to maintain the accuracy and reliability of the method. So this type of test is not or will not be suitable for very fine grained soil like silt and clay. So in that case we have to take the help of another test, laboratory test called falling edge permeability test, that we will see in the next problem. Okay, however, for this kind of test you should keep in mind that this type of test is basically uh, feasible or suitable for coarse grained soil where we can maintain a constant head and a sufficient or adequate amount of water can be collected over a specific time span. For example, here the time span is 1 minute of testing, and the amount of water which is collected or which was collected is 945.7 gram. So next we'll note down the constant head. If we mentioned it as H, so this is 75 centimeter, and the time of testing is 1 minute, and the water which is collected, so we'll write it as volume in terms of volume, so it will be 945.7 cc. Okay, since you know that the density of water is 1 gram per cc, so if you basically means from the definition that rho equals to W by V, so W and rho you know, so you can easily calculate the volume. That volume will be simply mass. Okay, so mass divided by density. Here density is 1, so that's why mass and volume will be equal. So 945.7 cc. Okay, now what we'll do, we will have to calculate the coefficient of permeability, that is nothing but K. Okay, so this is the question asked to this problem. Now how can we calculate? So we'll go back to the Darcy's law. So that's why I mentioned it at the very beginning of this session. So it's a very useful law specifically for flow through soil or porous media like soil. So we'll go back to the Darcy's law. Now what is Darcy's law? So as per Darcy's law, this V is proportional to I. So velocity of flow is proportional to the hydraulic gradient. So if we use a proportionality constant K, that is nothing but the coefficient of coefficient of permeability, or we can say hydraulic conductivity, and this I, this is hydraulic gradient, and this K, this is this V, this is velocity of flow. So as per Darcy's law, velocity of flow equals to K times I, that is hydraulic conductivity times hydraulic gradient. So this is the velocity of flow. Then we can easily determine the rate of flow. So the rate of flow, it would be A cross sectional area times B. So this is the rate of flow. So this is the rate of flow. Now what will be the total flow? So total flow, so for that we have to multiply this rate of flow with the corresponding time, okay, corresponding duration. So Q, it will be Q into T. That means A VT, that means A KI T. So this is the total flow, and this is the final equation we have. Now if you observe very carefully, so in this equation, all the means among these 5 entities, okay, so Q equals to, we can say, K I A T. If we reorganize this equation, now as you can see in this equation, a total of 5 entities are involved, okay. Which are those entities? The total flow Q, the hydraulic conductivity K, hydraulic gradient I, cross sectional area A, through which the flow is basically happening, and the time duration T. Now among these 5 quantities, only one entity, among these 5 entities, only one entity is unknown, and that is the hydraulic conductivity. Otherwise, all the 4 entities are known to us, such as Q, I, A, and T. So we can easily determine the hydraulic conductivity of the soil by using this equation, okay. So how, that we'll see subsequently. So this K, we can write Q upon I A T. Now what is I? I, this is the head loss per unit distance of flow, okay. So that means H upon L. This is the head loss divided by the distance over which the head is lost, okay. So that is called hydraulic gradient. Then what is A? So since the sample is basically cylindrical in shape, so the cross sectional area, this would be pi by 4 d square. Now this is the modified expression for K based on constant head permeability test. Now we'll simply substitute the given values in this equation, okay. So after substitution, it would be 945.7 cc. What is about H? H is 75. This is the constant head maintained during the test. What is the length of the sample or height of the sample? 16.8. Okay, over which this head difference exists. And then the cross sectional area, so pi by 4 into d square. The diameter of the sample is 7.3. And the time of testing is 1 minute, so that means 60 seconds. So if you calculate, then you can easily get the hydraulic conductivity of the given soil sample. So it's 0 point, or we can say 8.4 into 10 to the power minus 2 centimeter per second. However, we have to report the hydraulic conductivity in meter per second. So that's why we have to divide this value by 100 to get it in meter per second. So 8.4 into 10 to the power minus 4 meter per second. So this is the final answer to this question. The hydraulic conductivity is 8.4 into 10 to the power minus 4 meter per second. Okay. So this is an example through which we have seen how to utilize the data of a constant head permeability test to determine the hydraulic conductivity of a given soil sample. So for that, what are the required data? The sample dimension you should know, the constant head you should know, and the total amount of water collected and the time of testing. So these two information also you should know. So if or once you have all this information, you can easily determine the hydraulic conductivity of the given soil sample. Okay, so based on Darcy's law. Okay, I hope this is fine to all of you. Now we'll proceed further and we'll take the next example problem. Okay, 1 minute. Okay, sorry for the interruption. So we'll take this second problem for this session. So in this problem, a falling head permeability test was performed on a sample of silty sand. the time required for the head to fall from a given value to half of that value in the standpipe was 1.5 minutes. The cross-sectional area of the standpipe was 6.25 centimeters square. If the height and diameter of the sample were respectively 16 and 4 centimeter, determine the value K in centimeter per minute. So again, in this problem as well, we have to calculate the hydraulic conductivity K of the sample, of the tested sample, that is a sample of salty sand. However, considering the data of a falling head permeability test. Okay, and by that time you know that why this kind of falling head permeability test is required over the constant head permeability, because constant head permeability test is specifically suitable for coarse grained soil, so that we can collect an adequate or sufficient amount of water for a for an accuracy and reliability of the test or measurement of the K value. However, when this condition is not fulfilled, like very fine grained soil, so in that case we have to take the help of falling head. So we only observe the difference or the fall in the head. Okay, so if we draw the schematic for this falling head permeability test, so it will look like, so suppose this is the, sorry, this is the sample of length L. So this is connected to a standpipe of diameter A. So this is the standpipe, this is the sample. Now at the beginning of the test or before the test, suppose this is the level of water, or this is the head was available, and at the end, suppose this is the head remains available, and between this H1 and H2, at intermediate time, suppose this is the head. So what you need to do, you have to just basically measure the fall in head at different time interval. So this standpipe is basically graduated. So once the flow is basically happening through this sample, so there will be a loss or there will be a fall in this head in the standpipe. So that fall you have to basically record at different time interval, and only a pair of data, that is two observations, are required to calculate the hydraulic conductivity, that we will see. However, for a better accuracy, you can calculate the K considering this pair, several number of pair, and then you can take an average of these values for a better accuracy of the measurement. Okay, so this is the fundamental or fundamental principle behind this test. Okay, so now we'll again go back to the uh, Darcy's law. So as per Darcy's law, we can write Q equals to K I A. So K is the Hadley conductivity, I is the Hadley gradient, and A is the gross cross-sectional area perpendicular to the flow of direction through which the flow is basically occurring. Okay, and this flow, rate of flow, can be equated to the fall in the standpipe. So if the cross-sectional area of the standpipe is A and there is a fall in the head in the standpipe by dH amount over a time dt, so the rate of flow would be again A. So this is the cross-sectional area multiplied by this velocity dH by dt. Now why this negative sign is there? This negative sign indicates that with due course of time the head is basically decreasing. So to indicate the decreasing trend, a negative sign is basically used here. So this is the this is the flow through the soil sample, and this is the rate of flow through the soil sample. This is again the rate of flow through the standpipe, but both flow means should be equal. Okay, so this is from the soil sample and this is from the standpipe. Now if we rearrange this equation, that is K, this I can be written as H upon L multiplied by A minus A dH dt. So this is the, okay, we'll write down these notations at the end. Okay, so then this would be minus dH by H now if we integrate H1 to H2 and here Ka by L dt t1 to t2. So this would be A times ln h1 by h2, considering the minus sign, and this would be K by L t2 minus t1. So therefore this K should be 2.3 AL divided by A t2 minus t1 log of h1 divided by h2. Okay, so this is the final expression of hydraulic conductivity based on falling head permeability test. Here A indicates the cross-sectional area of the standpipe, which is given as 6.25 centimeters square. 6.25 centimeters square. Then capital L, this represents the length, or we can say the height of the sample. Okay, So height of the sample, which is given as 16 centimeter. Then A, capital A, this is the cross-sectional area of the sample. Now, what is the cross-sectional area of the sample? The diameter of the sample is given as 4 centimeter, and the cross-sectional area would be pi by 4 times this square. So that means pi by 4 times 4 square centimeter square. Now, what's about this h1 by h2 and t2 minus t1? So, t2 minus t1, this is the time frame over which the fall of head is basically measured. Now, the time required for the head to fall from a given value to half of that value in the standpipe was 1.5 minutes. So, the difference in time, so this is 1.5 minutes, okay, t2 minus t1. So, this is 1.5 minutes. And over this time, the head which was basically available at the beginning, so that is basically reduced to one half to its original value. So that means h1 by h2 is basically 2. Okay. So as per the problem statement, the time required for the head to fall from a given value to half of that value in the standpipe was 1.5 minutes. So over this time, t2 minus t1, that is 1.5 minute, the initial head is basically reduced to its half value, okay, to its half. So that means these are the data given to this problem. Now we have to simply substitute these values in this equation. So only after that we can determine the hydraulic conductivity of the given sample of silty sand. Okay, so 2.3, the cross sectional area of the standpipe is 6.25 centimeter square. The height of the sample is 16 centimeter. Then the cross sectional area of the sample is pi by 4 into 4 square. T2 minus T1 is 1.5 minute, and H1 by H2 is 2. So please calculate and let me know what is the answer for this K value. So it would be 3.67 centimeter per minute. So please be very careful about the unit. So I didn't convert the T from minute to second. Why? Because the final answer should be reported in centimeter per minute. So that is the answer. Okay. So for the given data pertinent to a falling head permeability test performed on a sample of silty sand, the hydraulic conductivity of the sample is 3.67 centimeter per minute. So for the examination purpose, you can recall the final expression which we have derived from the basic fundamentals. Okay, so that means from the Darcy's law. So if you can recall, it's fine. Otherwise, you have to derive this expression from the very beginning, that is considering the Darcy's law and the fundamentals or the principle behind this kind of test. Okay. So is it fine? Is it fine? Okay, assuming so, we'll proceed further. So we'll take this problem 3. So in this problem, laboratory test on a sample of undisturbed silty sand gave the following data: water content equals to 15%, specific gravity 2.62, degree of saturation 78%, this hydraulic conductivity value is 6.28 into 10 to the power minus 2 centimeter per second. So we have to estimate the value of K of another similar sample whose unit weight is 16.5 kilonewton per meter cube and having same degree of saturation. Now please try to understand the problem statement. What is written in this question? So basically, the hydraulic conductivity of a sample is given with the data. So if we summarize the data, if we summarize the data for two samples, the first one is sample 1 and the second one is sample 2. Now for sample 1, water content is given as 0.15. The specific gravity of soil solids is given as 2.62. The degree of saturation is given as 0.78. The K value is given as 6.28 into 10 to the power minus 2 centimeter per second. So these are the data given for sample 1. Now what are the data given for sample 2? Only the bulk unit weight gamma B is given as 16.5 kilonewton per meter cube and it's having the same degree of saturation, that is S remains constant for sample 1, both sample 1 and sample 2. So it's 0.78 and you can take the specific gravity value also same. It's a similar sample. Since it's a similar sample, the specific gravity of soil solids also you can take it the value for sample 1. Okay. Now what we have to determine? We have to basically determine the K value for the second sample, whereas the K value for the first sample is given. So therefore, first you need to identify the controlling parameter or the factor which is affecting or which would be the possible reason behind the variation in the void ratio for these two samples. First you have to identify that factor. So whether the void ratio would remains whether the permeability value, the hydraulic conductivity value or the coefficient of permeability would remain same for both the samples. If so, then okay, it's absolutely fine. There is no need to identify the factor which can affect the variation in the hydraulic conductivity for these two samples. But if that is not the scenario, then you have to first identify the factor which can affect the hydraulic conductivity from in sample 2 as compared to sample 1. Now, considering the given data, it's quite obvious that the possible factor which can affect the hydraulic conductivity here, at least for this problem, is nothing but the void ratio. Now, why we can or how we can identify this factor? So that remains or that depends on the basic relationship, okay, which we have got from the three-phase relationship or three-phase diagram of a given soil. So first of all, the void ratio of sample 1 can be calculated by using this equation. E equals to WGS by S. Here the water content you know 15%, GS you know 2.62 and the degree of saturation you know it's 0.78. So this is E1. Again, gamma B, the bulk unit weight. What is the expression? GS plus AC divided by 1 plus C multiplied by gamma W. So you know GS, you know S, you know gamma B, you know gamma W. So again you can determine the E2 value. Now you have to check whether these two values are same or not. If same, then there should not be a variation in the void ratio for these two samples. Sorry, hydraulic conductivity for these two samples. Otherwise, you have to calculate the hydraulic conductivity value for sample 2 separately, because you know what are the possible factors which can affect the hydraulic conductivity of a soil sample, like the uh, properties of the soil matrix, grain size distribution, then the pore structure, then the viscosity of the pore fluid, and the void ratio. So these are the factors which can affect the hydraulic conductivity of a sample. Now among these, as you can see from the given data, that the E value would be different for these two samples, so E1 and E2. So we can only conclude that, so when we'll be able to calculate these two E values for the given two soil samples E1 and E2. So we'll first do that, and then we'll see whether E1 and E2 are different or same. Okay, accordingly we have to calculate the hydraulic conductivity for sample 2. Now E1 we can easily calculate. So W is 0.15, then GS is 2.62, and the degree of saturation is 0.78. So if you calculate, then this value would become 0.504. So this is for sample 1. The void ratio of sample 1 is 0.504. Now for the same for sample 2, we can calculate in a different way, because here these data are not given, instead the bulk unit weight is given. So 16.5 equals to 2.62 plus 0.78 E2 divided by 1 plus E2. So unit weight of water we are taking as 10 kilonewton per meter cube. Okay. Now if you simplify this equation, so it would become, or it would look like this. So 1.65, so that means 1.65 minus 0.78 E2 equals to 2.62 minus 1.65, or E2 value you can calculate 0.97 divided by 0.87, that means 1.11. So it's quite clear that the void ratio values for the two given samples are not same, they are different. So first of all, for sample 1, the U1 value is 0.504, and for sample 2 it is 1.115. So almost twice of that for sample 1. So the void ratio of sample 2 is twice of that for sample 1. Okay. So then what we need to do to calculate the hydrolytic conductivity for sample 1, because we know the hydrolytic conductivity of sample 1. So sample 1 is 6.28 into 10 to the power minus 2 centimeter per second. We need to figure out the value of K2. So what should I, or what should we do for the calculation of K2, where E1, E2 and K1 are known to us? So we can utilize one empirical relationship given by Taylor. Okay. So first I'll write the statement. So to predict for a given soil sample, the value of K at a void ratio other than the one at which it is determined. So the same problem we are facing here. So we are trying to predict the value of K for a given soil sample and at a void ratio which is different than the K value where it is measured. So the K value which is given to us 6.28 into 10 to the power minus 2 centimeter per second. It's measured at a void ratio value of 0.504, and now we have to predict the K value for a different void ratio value of 1.115. So if this is the scenario, then we can utilize the empirical relationship between the hydraulic conductivity and the void ratio given by Taylor. Okay, so Taylor recommends the following relationship. That the ratio of these two hydraulic conductivities K1 is to K2, it would be C1 E1 cube divided by 1 plus E1, then C2 E2 cube divided by 1 plus E2. Now what are these C1 and C2? So C1 and C2, so these are the shape factors which depend on the manner of packing of the grains and the shape characteristics of the pores. Of the pores. However, it was found that for sand, C changes very slightly with the void ratio. So for sand, C changes, the shape factor changes slightly with void ratio. That means we can take C1 and C2 both as equal. Okay, so this is the implication of this statement, that for sand C changes very slightly with the void ratio. So we can take C1 and C2, both the values are equal. So therefore this ratio K1 by K2 would become Q1 cube by 1 plus C1 divided by E2 cube by 1 plus E2. Now from this onward, it would become very easy to calculate the value for K2, because E1, E2 you know, K1 you know, just we have to substitute the values in this equation. So once you substitute, you can easily get the value of K2 as okay. So Q1 value is 6.28 into 10 to the power minus 2. E2 is 1.115. E1 is 0.504. Now if we calculate this expression, so it's 0.48 approximately centimeter per second. So this is the answer. Okay. So the past two problems, we have seen the application of data obtained by constant head permeability test and the falling head permeability test respectively. And in this problem, we have seen the application of an empirical relationship given by Taylor to calculate the hydraulic conductivity of a sample, where the hydraulic conductivity of another similar sample was given, but for a different void ratio value. Okay, so is it okay? So it's a very straightforward problem. Just you have to determine the void ratio values for the two given soil samples, and these values are 0.504 and 1.115 respectively, at least for the given problem or given data. And then we have to utilize the relationship, the empirical relationship given by Taylor, to predict the value of K for a given soil sample at a void ratio other than the one at which it is determined. Okay, so based on this relationship, we have calculated the hydraulic conductivity for sample 2 as 0.48 centimeter per second, where the hydraulic conductivity value for sample 1 was given as 6.28 into 10 to the power minus 2 centimeter per second. Okay, so if it is okay from your end, then we can take the next problem, problem 4. So in this problem, for the test arrangement shown in figure 1, calculate the volume of water discharged in 15 minutes. The cross-sectional area of the soil is 3500 millimeter square and the K value is 2.5 millimeter per second. So uh, this question or this problem is basically a modified version of the constant head permeability test. So earlier in problem 1, the K value was not given, rather we had to determine the K value, where the volume of water collected over a specific duration of time was given. So it's a opposite an opposite or reverse scenario to the problem formulated in question 1. So in this case, we have to determine the volume of water discharged in 15 minutes, where the K value is itself given. So this is the only difference between the two problems, that are problem 1 and problem 4. But again, we have to use the principle of constant head permeability test based on Darcy's law. Okay. So if we calculate, if we have to calculate the volume of water discharged in 15 minutes, first we need to know the rate of flow from Darcy's law. Q equals to K I A, where I is H upon L into A. Now we'll figure out these entities one by one. Now what is the K value given to this problem? The K value is given as 2.5 millimeter per second. The head difference, the constant head. What is the constant head given to this problem? So this is the difference between this inflow and outflow. So these two levels, the difference between these two levels will give you the constant head difference for this problem. Now, what is the head? If we take this is as datum, so this is the datum. So at point A, so if we denote this point as A and B, sorry. So at A, so it will be 225 plus 375. Okay. So summation of these two values. So this is the head at A minus head at B. So that is only 150. So if we subtract this 150 from the summation of 225 plus 375, that will give you the constant head for this setup or configuration. So this is 450 mm. Now this 450 mm head was lost over how much length? Over this length. Okay. So if we use a different color, so this is the length. So over this length L, so this much head, 450 mm head was lost. Now how to calculate this value L? So it's a very simple trigonometry law, or from the trigonometry we can calculate. So this is the triangle. So the perpendicular and the base value you know. So you can easily calculate this dimension. So this would be 300 mm. So this is the base value and this is the perpendicular. So 225 square plus 300 square. Okay, this will give you 375 mm, and the cross sectional area it's given as 3500 mm square. So these are the data which are required to calculate the volume of water discharged in 15 minutes. Okay, so we'll now substitute these values in the equation. So K value is 2.5, then H upon L, that means 450 by 375, multiplied by 3500. So that means millimeter cube per second. So 1.05 minus 10 to the power minus 5, 1.05 into 10 to the power minus 5 meter per second. So this is the rate of flow. Now we are considering the discharge over a duration of 15 minutes. So therefore the total volume, so it would be Q multiplied by T, 1.05 into 10 to the power minus 5 into 15 into 60 meter cube. So that means 9.45 into 10 to the power minus 3. So additional data is given as 15 minutes. Okay. So it's a reverse problem to problem 1. Here you have to calculate the volume of water discharged in 15 minutes, where the cross sectional area of the soil and the hardly conductivity of the soil are given, and at the same time the configuration, that means the soil dimension, is given but in a different way. So this here the trick lies. Okay, so we have to calculate the length of the sample very carefully, and the head, constant head between the inflow and outflow, very carefully. So this is the only job which is basically given to you, that you have to calculate the H value and the L value. So H, so it's you can calculate in this manner, that first you calculate the head at inflow, means at point A, and head available at B, and take the difference between these two. So that is the constant head maintained throughout the test. And for length, length of the sample, so you know this dimension, you know this dimension, so it forms a triangle. So from this triangle, you know two sides of the triangle, so you can easily calculate the another side of the triangle very easily. So then you implement the Darcy's law, will first have the rate of flow, and you know the time duration. So if you multiply the time duration with the rate of flow, you can easily get the total flow over the time duration. Okay, so this is the answer. Now we'll take the last problem for this session. So this is related to a stratified deposit. So figure 2 shows 3 layers of soil in a tube that is 100 millimeter by 100 millimeter in cross section. Water is supplied to maintain a constant head difference of 300 millimeter across the sample. The hydraulic conductivities of the soils in the direction of flow through them are as follows. So with this data, we have to find the rate of water supply in centimeter cube per hour. So in this problem, so uh, it's not a case of only one soil sample. Rather, this problem involves three different soil samples: soil sample A, soil sample B, and soil sample C. And for all these three soil samples, the hydraulic conductivity values are different. For example, the hydraulic conductivity of soil sample A is 10 to the power minus 2 centimeter per second. For B, it's 3 into 10 to the power minus 3 centimeter per second. And for C, it's 4.9 into 10 to the power minus 4 centimeter per second. So from A to C, from sample A to C, the hydraulic conductivity value decreases continuously. Okay, so with this configuration or with this kind of problem statement, you need to determine or calculate the rate of water supply which is basically happening or occurring through the soil samples. Okay, so first we need to identify the direction of flow. So this is the water supply and this is the outflow. So that means it's quite obvious that the flow is happening in this direction. Okay, so flow is happening from left to right, and for that, so this constant head difference of 300 millimeter is basically responsible. So for water to flow from this left to right, this constant head difference of 300 mm is responsible. Okay, so how we can determine? So we can easily determine this rate of flow if instead of 3 samples only 1 sample was given. So how? By implementing Darcy's law. So as you can feel, in all of these 5 problems we are again and again using Darcy's law. So it's a very essential when you will be dealing with permeability in soils or porous media like soils. Okay, so Darcy's law you have to implement for determining the rate of water supply. So Q equals to KIA. Now A, you know, the cross sectional area, the gross cross sectional area perpendicular to the flow direction, so that is 100 mm by 100 mm. You know the I, hydraulic conductivity value. How you know the hydraulic conductivity value? Because this is basically the total head lost divided by the distance over which this head is lost, and the constant head difference between the two entry and exit points, you know, 300 mm, and the length over which this constant head difference prevails, that also you know. So it is nothing but a summation of 150 mm, 150 mm, and 150 mm. So this is the total length. So therefore 300 by 450, so that will give you the Hartley conductivity, Hartley gradient value. Now what's about K? So K, you cannot choose a single value because here 3 different values are given for 3 different soil samples A, B and C. So again you can use only a particular soil sample, but for that you have to uh, precisely choose the I value, the Hadley conductivity value. So that will be different because between the two ends of sample A, the Hadley conductivity is having a value, suppose I1 or IB, IA. For B, between the two ends of B, you are having a Hadley gradient IB, and similarly for C, we will be having an hydraulic gradient IC. So these hydraulic gradient values will be different depending on the soil sample. However, the rate of flow should be same through all the soil samples. So whatever flow is basically occurring through sample A, the same flow will be occurring through sample B, and again the same flow will be happening through sample C. So this is from the continuity equation. So the same flow is basically occurring through all the soil samples. However, here the hydraulic gradient value will be different depending on the soil sample. Okay, so that's why to simplify our calculation, we have to take the help, or we have to basically depend on the concept of equivalent hydraulic conductivity for a stratified deposit. Equivalent hydraulic conductivity for the stratified deposit. So please note a point here. So either you can recall the expression, the final expression for the equivalent hydraulic conductivity, otherwise you can derive it from the very beginning or from the fundamentals. Okay, so that will do for this problem here. So we'll first define this conductivity values. So sample A, sample B, sample C. Now for length, sample A is having 150 mm, sample B is again having 150 mm, and sample C 150 mm. So all the samples are same size. Okay, so 150 mm. Then Ka. So Ka, so this is 10 to the power minus 2 centimeter per second. Kb, it's 3 into 10 to the power minus 3 centimeter per second, and Kc, it's 4.9 into 10 to the power minus 4 centimeter per second. And lastly, the head lost over sample A, we are denoting as HA, for sample B HB, and for sample C HC. Now, as you know that the rate of flow is same throughout the soil samples A, B and C. So the Q is same, QA, QB and QC. So these are basically head loss. Now since the cross-sectional area of all the three samples are again same, so therefore your V, the velocity of flow, would be same. However, the total head is a summation of all the three head losses. So the total head loss is a summation of all the three head losses, which are basically taking place individually for sample A, sample B, and sample C. Now, from the Darcy's law, you know that V equals to Ki. Again, this I is nothing but H upon L, head loss by length over which the head is lost. So therefore, this V you can equate to VA. VA means KA HA by LA. You can equate it to the velocity of flow through soil B. So KB HB by LB, and finally KC AC by LC. So you can observe that a separate notation is used here to indicate the head loss. So instead of small h, we are using capital H because this HA or HB is already used in this figure. Okay, so that's why. Now you can represent this head loss HA, HB, and HC. So HA, or rather this K, you can write it as K equivalent. Okay, K equivalent. So HA you can write when you are basically considering these two terms. So what is HA? So it will be K equivalent into LA by HA into H by L. So similarly, you can calculate HB. So it will be K equivalent LB by HB H upon L. And similarly for HC, K equivalent LC by HC H upon L. Now you can substitute these values here. So in this equation, so okay, 1 minute. Okay, so so you can substitute these values for HA, HB and HC in this equation. So how, that we'll see in this slide. So first of all, you can write H as K equivalent okay, sorry, you leave it. So you simply write H, okay, equals to, if we take this common, K equivalent H upon L, so K equivalent H upon L, then inside the bracket would be LA upon HA plus LB upon HB plus LC upon HC. Therefore, this H and H will cancel out and K equivalent would be L divided by LA upon, okay, sorry, I think I made a mistake here. So here we are writing HA, na? So this would be, sorry, this would be KA, this would be KB, and this would be KC. So this is the final expression for equivalent hydraulic conductivity for the given problem. So that means the total length, including the length of all the three samples, LB, LA plus LB plus LC. So this is the length of sample A, sample B, sample C, and these are the hydraulic conductivities of sample A, sample B, and sample C respectively. So as I mentioned at the beginning, that either you can recall or you can memorize this expression for the examination purpose, or you can derive it from the fundamentals. Okay, so therefore the next job is to substitute these values to get the hydraulic conductivity. So L, so this is 150 plus 150 plus 150. So this is the total length, and these are the individual length, 150 by 10 to the power minus 2 plus 150 by 3 into 10 to the power minus 3 plus 150 by 4.9 into 10 to the power minus 4. So if you calculate, then this would be 450 divided by 150 by 10 to the power minus 2 plus 150 by 3 into 10 to the power minus 3 plus 150 by 4.9 into 10 to the power minus 4. So that means 1.213 into 10 to the power minus 3 centimeter per second. So this is the equivalent hydraulic conductivity. Now you know the equivalent hydraulic conductivity. So that means you can use Darcy's law and you can easily calculate the rate of water supply. So Q K equivalent, I is H upon L into A. Now K equivalent is your 1.213 into 10 to the power minus 3. H is your 150, sorry, 300. The head difference, the constant head difference, so this is your H, okay, divided by the total length, 150 plus 150. So this is the length, total length L, multiplied by the cross-sectional area. The cross-sectional area, so this is the cross-sectional area, 100 into 100. So please note that this hydraulic conductivity, equivalent hydraulic conductivity we have obtained in centimeter per second, whereas this A is in millimeter square. So that's why you have to multiply it with 10 to the power minus 6 to get it in, sorry, 10 to the power minus 2 to get it in centimeter square. So it's 0.0809. So it's 0.0809 centimeter per second. However, we have to report the rate of water supply in centimeter cube per hour. Okay. So this is the requirement. So therefore, we have to convert the unit. So key centimeter cube per second to centimeter cube per hour. So for that, we have to multiply this with 3600. So 291.24 centimeter cube per hour. So this is the answer. Okay, so we'll recollect all the steps which we have followed for this problem, problem 5. So first of all, we applied the concept of equivalent hydraulic conductivity for a stratified deposit. Now, why it's a stratified deposit? Because all the samples, all the three samples are not having the same hydraulic conductivity value. Rather, the samples are having three different hydraulic conductivity values as 10 to the power minus 2 centimeter per second, 3 into 10 to the power minus 3 centimeter per second, and 4.9 into 10 to the power minus 4 centimeter per second for soil sample A, B, and C respectively. Okay, so that's why we applied the concept of equivalent hydraulic conductivity for this kind of stratified deposit. Now then, two physical conditions we need to consider. So the first one is the velocity of flow is same for all the three samples. Why? Because the rate of flow is same for all the three samples. Since the rate of flow is same for all the three samples and the cross-sectional area is also same or remains same for all the three samples, so from the basic fundamentals, so the velocity of flow should remain same for all the three samples. So this is first condition. Now coming to the second condition, the constant head difference 300 millimeter. So this is a summation of head lost, individual head lost occurred for these three samples A, B, and C. Suppose HA, capital HA head is lost for sample A, capital HB is lost for sample B, and capital HC is lost for sample C. Then the summation of HA, HB, and HC will give you the value of total H, that is 300 mm. So based on these two conditions, And considering the Darcy's law, we have derived the expression for equivalent hydraulic conductivity of the given stratified deposit. And by substituting the given values, we have obtained the hydraulic conductivity value as 1.213 into 10 to the power minus 3 centimeter per second. So, since the equivalent hydraulic conductivity value is known to us, so we can easily determine the rate of flow through the soil samples. So for that, we need to know the constant rate difference, the total length, and the cross-sectional area. So the total area is 300, the length is 450 mm, and the cross-sectional area is 100 by 100 millimeter square. So first we converted the millimeter square to centimeter square, then we converted the centimeter per cube per second, this unit of rate of flow, to centimeter cube per hour, because this was required for reporting the final answer. So in this way, we have solved problem 5. Now we'll end today's session with this homework problem. So in this homework problem, a permeability pumping test was carried from a well sunk through a surface layer of medium dense sand, as shown in figure 3. Initially, the water table was located at a depth of 2.5 meter. So this is the water table. Okay. So this is the water table at a depth of 2.5 meter before the test located. Now, when a steady state pumping was achieved at the rate of 20 meter cube per hour. So this is the steady state pumping at a rate of 20 meter cube per hour. The following drawdowns were observed. Pumping well, the drawdown is 4 meter, so this value. Then observation well 1, so this is observation well 1. The drawdown is 1.5 meter, so this value 1.5 meter. And the observation well 2, the drawdown is 0.5 meter, so this one. Okay, so all these values are in meter. Now, what is the coefficient of permeability of the sand? So this is a typical example of determination of coefficient of permeability considering or based on field test. What kind of field test? Pumping out test. Okay. So for that, you should again go back to the Darcy's law, that is Q equals to KIA, and here this I, for this I, what you need to do, you have to basically consider an imaginary soil cylinder of thickness of radius r, thickness dr, and this height is h, and this difference is your dh. So therefore the hydraulic gradient would be dh upon dr, and what would be the A? The surface area of the cylinder, that is 2 pi r h. Okay. Now what you need to know, you have to basically reorganize this equation and then you have to apply the integration. Okay. So dr by r k 2 pi k h dh. Now you integrate this R2 R1 and H2 to H1. So if you integrate, then this would become ln R1 by R2, and on the right hand side pi k H1 square minus H2 square k. So this would be q ln R1 by R2 divided by pi H1 square minus H2 square. So this is the final expression of Hadley conductivity based on this pumping out test. Now, what are these values? This R1, R2, H1, H2, Q. So Q, obviously the Q is the steady rate of pumping. So that means 20 meter cube per hour, and this R1 and R2, these are the radial distance of the observations well from the test well. So this is the test well, and these two are the observation wells. Okay, so the radial distance of observation wells is denoted by R from the test well. So therefore this R1, the radial distance of test well 1 from the observation well, what is the distance? The distance is 20 meter. So this value. Then R2, what is the radial distance? The radial distance is 60 meter. The radial distance of observation well 2 from the test well. So this is 60 meter. And coming to H1 and H2, so this is basically drawdown water table. Okay, so this is called drawdown water table. So the height of drawdown water table from the impermeable base. So for H1, for test well 1, so this height you have to determine. So this is H1 and this is H2. So to determine that, first we'll calculate the value of H0. So that means the initial water table location from the impermeable base. So what is the value of H0? So it would be the total thickness minus the water table location from the ground surface. So that is 2.5. So 10 minus 2.5, that is 7.5 meter. Now to calculate H1, that is the height of drawdown water table from the impervious base in test well 1. So you have to subtract this value, this drawdown value from this H0. Okay, so H0 minus D1. So H1 would be H0 minus D1, and similarly H2 would be H0 minus D2. So H0 is 7.5, D1 is 1.5, so that means this is 6 meter, and for test well 2, it's 7.5 minus 0.5, that is 7 meter. Okay. So this completes the data which are required for calculating the Hadley conductivity value. Now I will not solve this problem anymore. So it's a homework problem. So I will leave this problem here. So please solve the problem entirely at your home. Okay. Now from this onward, please solve and let me know if you face any difficulties while solving this problem in the next session. I uh, I hope there should not be any difficulties because we have already derived the expression for hydrogen conductivity, and we have also summarized the data which are required or which are involved in this expression. So just you have to substitute all this data appropriately in this expression, and then you can easily get the hydrogen conductivity value. Okay, so with this we'll end this session here. Now before doing that, let us recollect all the problems which we have solved in this session. So first we have started with a problem related to constant head permeability test. Then we have come to another problem related to falling head permeability test. So in those problems, we mostly determine the hydraulic conductivity depending on the test data. Okay, so for example, uh, utilizing the data of constant head permeability and the data of falling head permeability, we have determined the hydraulic conductivity of the given soil sample. Now coming to third problem. So in this problem, we have seen the application of an relationship given by Taylor to calculate the hydraulic conductivity value for a soil whose void ratio value is different than a soil uh, for which the hydraulic conductivity was given. Okay, so that means we have seen the effect of void ratio. Indirectly, we can say the how does the void ratio affect the hydraulic conductivity. Now coming to fourth problem, so this is a reverse problem of problem 1. So in problem 1, the volume of water collected over a specific time duration was given and we had to determine the hydraulic conductivity, but here hydraulic conductivity is given. We have to or we had to calculate the volume of water discharged over 15 minutes time duration. So again we have implemented the Darcy's law and we have calculated the uh, discharge in 15 minutes, the volume of water discharged in 15 minutes. Then in problem 5, we encountered a stratified deposit, and in this case, we have determined the equivalent hydraulic conductivity, and then we have again implemented the Darcy's law to calculate the rate of water supply through this stratified deposit. And finally, we have taken on homework problem. So this is an example of field permeability test by pumping test. So for this kind of test, initially we have derived the expression of hydraulic conductivity, and then we have summarized the data, test data, and the portion which is left over you, that is the calculation of hydraulic conductivity by substituting the data in the final expression appropriately. So this is a summary or overview. This is an overview of today's session. Now we'll stop here and we'll wait for a few minutes. So if you have any questions or if you need any further clarification or discussion, please let me know. And thank you for joining this session. Have a nice day. Okay, so for your kind information, we'll again meet on next Friday. Okay, so instead of Sunday, so the information will be conveyed to you through a mail. So we'll meet again on next Friday, that is on 23rd February at 6 p.m. So the next session is basically rescheduled. So that information will be conveyed to you in the due course of time through the mail conversation. Okay, so I am assuming there are no questions and ending this session here. Okay, so thank you again for joining this session.